back to our last day of the week. It's our Friday, I guess, a Wednesday that's a Friday. We have a holiday on Friday. What we are going to enter into at this point is the last section of the course where we just sort of do everything backwards. If you're good at doing things backwards, great. If not, we're going to learn some of these techniques, and we'll use several different names. We're going to start off calling it an antiderivative, or as you'll see, I'll call it an underderivative, the thing before the derivative. We'll later on call it an integral. We'll call it and there's a definite integral and an indefinite integral, but they all have basically the same thing that we're trying to do. We'll discuss what it really means, but think, what is a derivative? It's a slope. It's a rate of change. So what would the thing before the derivative be? The result of that sort of rate of change. So what you'll see is it's actually accumulation. So the one before it becomes some sort of values, the derivative is the rate things are changing. The thing before the derivative is actually an accumulation. Like think of a garden hose going off, how much water fills up. Derivative is the rate that the water's coming out. The integral is how much water we end up in the puddle. Okay, so it's kind of, those are the two things we get with calculus. We get a rate, a slope. That's the derivative. We've been working on all of that. If we start with the derivative and go back to the other function, what we're getting is how things accumulate, how that rate affects things. And again, a lot of times, what we're able to measure in a situation is the rate. We're not able to measure how much is out there. So leaking oil tanker, they can measure how fast the oil is coming out of it, but once it's out in the ocean, they can't really measure what's out there. So they have to use this process to figure out, okay, it started leaking here, it's at this rate, that's about how much is out there. So that's what these techniques are going to help us solve, problems where we can measure the rate, but we don't necessarily get the other part. Driving your car, you can measure your slope by what's that thing called? Speedometer. Tells you how fast you're going, right? That's a rate. That's a slope. That's a derivative. If you want to figure out how far you've driven, then that's going to be the integral. Okay, so holiday on Friday, so try to remember that. Don't show up. Otherwise, you'll probably be lonely, or might be someone else who forgot too. But anyway, we can kind of spend the time to adjust back and everything. When we get back, we've got just 2 days to take a look at what we start building on today. So it's really going to be the same type of deal. We're just going to formalize it a little bit more, call it an integral, do some integration, which is the same thing we're doing today. We're just finding an antiderivative is what we're calling it today. Then we'll have some time to review this later stuff. We'll take our third exam, and then we just got 2 more sections, a review and a final. And again, and I'll have a discussion about this, but as far as the mastery test, we'll look to do it after we go through this, because by going backwards, it may help you to master taking derivatives a little bit better. And what I'm currently thinking of is doing have you take 20 derivatives and not have it multiple choice, so that you're not distracted by the wrong way of doing it. Having them to be sort of similar, but anyway, if you have other ideas, please feel free to talk to me and we'll go from there.
Wait, is that for the final, you're saying?
Well, it'll probably be during finals week. So, our final exam is set by the coordinators. I'm going to give a second version of the mastery test for anyone who wants to take it. You don't have to. Everyone asks, what if I do worse? Well, you shouldn't do worse, but if you do, we'll take the higher score. But you should do better, because by that time you've gone back and forth, and this time you'll just have to write down the correct derivative without having to guess what they did algebraically to get to the answer. Because I found that hard myself, is the negative here or there, or it gets confusing. So anyway, what we're doing today, let's backtrack a little bit to algebra. And just a warning, as we go through this, it's kind of a sort of a guess and check process. I will make some mistakes on the way on purpose, and because I want you to see what happens and how I can check and find that it was a mistake and then go back and say, oh, it was kind of a wrong way of thinking. So today's kind of to help you think through the process that we go through, and that when we go through the process, we don't always get it right the first time. But the thing is we have some techniques to check it, and in our check we say, oh, I was off, I thought it was this, and so we'll go forward with that. So what we're really doing, think of in algebra, what did you learn first? You learned something along, probably in high school, maybe middle school. We had a problem like this, and what do we do with it? FOIL it, right? Which stood for first, outer, inner, last. And so you took 2x times x, and you get 2x squared, right? And then you took 2x times -5 and got negative 10x. 4 times x plus 4x, and then 4 times -5 gave you negative 20. And then your final answer was 2x squared minus 6x minus 20. Then what did you do maybe a few years later, or a few chapters later, sections later? You sort of didn't get all of this information. You were given this, and you were told to do what? Factor, right? And what is factoring? It's putting it back how we got it. So it's the reverse of FOIL. So we might call it unfoil, okay? And remember, what I want you to think about is, how did you learn to factor? Now, some of us, it's not something I feel real proficient at. I can do it, yes, but it's still sort of a guess and check for me. Some people get down a specific method. They're able to look at it and do it just mechanically and get it always right. I'm not one of those people. So think about how you learned it and what worked for you, because that's the same skill set you're going to need to apply today as we go for antiderivatives, because we're doing basically the same thing. We're putting it back in the can, okay? And so again, you would say, oh, let's see. The way I would do it, okay, I know the first part comes from these two things multiplying to give me this. So must be one thing is 2x, the other thing is x. And then again, from doing a lot of FOIL, you see that last number came from multiplying the two last numbers. So I think, what are the factors of 20? 1 times 20, 2 times 10, 4 times 5. So see, I've got some options I've got to try out. I might choose the wrong one, and then, okay, then I FOIL it out, and I see that it didn't work, and so I do it again. So, and again, this is the way I do it. I always do a guess and check, and again, sometimes I don't. I see the middle is 6, and so what I've come to see is that since it's negative, one has to be negative, one has to be positive, which means we're going to subtract. So when I subtract the result, I need to get negative 6. And if I do 2 and 10, that gets me up to 20. I think I'm getting too big. Let's just try 4 and 5. And then you might put the 4 here and the 5 there. Well, that gives us 8 and 5. And no matter how you subtract 8 and 5, you get either 3 or plus or minus 3. That's not going to work. So then we say, okay, let's erase that or cross it out, because we don't want to spend a lot of time on this. I'll put the 4 here and the 5 there. So that gives me 10 and 4. And when I subtract them, I get 6. If I add them, I get 4. So I'm going to be subtracting them. I want it to be negative, so I want the larger value to be negative, so I'll put a negative here and a plus there, and then when we look back, we FOIL it out and we got what we started with. Okay. Similar process we're going to do today, except we're not foiling, it's not multiplication and sort of division. It's going to be a derivative and anunderivative. Okay, so we'll go through. That's the same type of process. It can be a little messy, at least that's the way it can be. We'll have a little chart out by the time we're done, so that will help us kind of make the right sort of intuitive guess, but we'll go. So what is an antiderivative? It's an underderivative. It's a function. So we start with a function which is a rate of change. function we're given is a rate of change. It means it's a derivative of something. And what we're trying to get is, well, what was it the derivative of? So again, we've been practicing. We started with a function that is a values function, and we're getting its rate function by taking the derivative. That's a forward process. What we're doing today is the backward process. So we're going to work backwards to find the function that the derivative came from. And we're going to look at this sort of function by function. So we'll start with a polynomial function. We'll look at some trig functions, some log and exponential functions, because they're each a little different. And again, this will be our beginning, and we will take a look at some others as we go. So this is a function we're given, and we're told to find the antiderivative. One of the first things I like to do myself is I say, okay, I'm going to put a little mark here to remind myself that this is a derivative. I put the derivative marker. And I want to find the function it came from. Okay, so just kind of see, this is a derivative. So I'm thinking, how did I get 3x to the 5th? I took an exponent, I multiplied it in front, and then I subtracted 1 from the exponent, right? How do I do that backwards? How do I do that as an inverse function? Think of inverse functions. Multiply, subtract 1. What's that? Add 1 first. So remember, inverses are always the opposite operation in the opposite order. So we are going to add 1 to the exponent, and then we're going to divide by that new exponent, not multiply by. So just think of that process, reverse process. So what I'm going to do is I know I need to add 1 to this exponent, and then I need to divide by that new exponent. So let's see. So that's going to give me x to the 6th, right? The 3 is just kind of coming along for the ride, and we'll see that it'll work. So then I get 6, and I need to divide by 6. Now, I'm not going to simplify this yet, because I'm going to check, and if I leave it as is, the check's going to work out. At least this is what I think I should have, because I'm doing things backwards. And again, I gave us really 3 processes. So how do I do this one? Add 1 to the exponent, and then divide by that new exponent. Okay, so I should have 5x to the 5th over 5. Okay, now what do I do with the constant? Is that just going to be 0? No, if I take the derivative of a constant, I get 0, but this is going backwards. What we want to think of this is really 2x to the 0 power. Remember, I kind of will write that down because that's 1 minus 1 equals 0. So x to the 0 is just 1. It's a way of writing 1. So now I do the same process, right? I add 1 here and divide by the new exponent, which is just 1. It's not a big deal, but I'm going to get 2x to the 1 power, and again, I'll write it over 1. Am I missing anything? Yeah, what am I missing?
You're missing plus c at the end.
Okay, there could have been a constant, because if there was some kind of constant number, if I took its derivative, it would be 0. So there's also a hidden plus 0 here somewhere, right? And so I don't know what that constant is, though, right? So good. So you maybe looked ahead. We're going to put a plus c, and again, this one I always forget to put this on. And fortunately, I had a teacher who understood. Some teachers don't. They say, "Oh, you didn't have the plus c. You're wrong." Plus c. Well, WebWorks might do that to you. I won't do it to you, but because eventually we're going to find ways to find what that is. But this is what my first guess is, that this is the sort of original function, and we'll use a capital letter F because that's what the textbook does. So this is the function it came from. We're suggesting. The way we go about checking, just like with FOIL, or factoring, we would factor it and then we would FOIL it just to check to see if we ended up with the right pieces in the right places. So now I come and say, okay, let's take this, let's take big F and take its derivative, see if we get the same thing. I get 6 coming down, but 6 divided by 6 is 1. So I get just a 3 here. I subtract 1 from the exponent, I get x to the 5th. Wow, that's what I started. I'm looking good on that first term. You see how that worked? Okay. The second one, I bring the 5 down. 5 divided by 5 is 1. There's still this 5 here. I subtract 1 from the exponent, I get x to the 4th. That's what I had here. Okay, so things are checking out good. I've got this minus 2x over 1. So again, I take the 1 down. 1 times 2 is 2. And then it get x to the 0, right? So I get 2x to the 0, or just minus 2. And whatever this constant is, whenever I take a derivative of a constant, I get 0. So it worked. Okay, so that's kind of the process as you do your best guess. Where you can probably have some of the problems is what coefficients you end up with, because there's sometimes already a number there, but just kind of go through. And then what we would say is for this one, our final answer, we'd maybe clean it up a bit. We'd say that the original function, 3 divided by 6, so that's going to be x to the 6 over 2. 5 divided by 5 is 1, so that's just x to the 5th. And then 2x over 1 is just 2x. And then we still have this plus a constant. Okay, so that's what the final answer would look like all cleaned up. You could take its derivative and you would see, yes, indeed, what we started with is its derivative. Okay, does that make sense? Feel comfortable? Okay. Let's get some things that aren't as comfortable. Go be, like, I don't know, get out of your comfort zone. Why? It's comfortable in there, right? Okay, trigonometric functions, a little less comfort. So what we have to do is, as we do these, again, remember, we are trying to think of this is our derivative, where did it come from? So it's, again, we're kind of getting back to having a good feel for what derivatives are. So remember, the function's output is a rate of change, and here's another function, and notice this is going to actually give us 3 opportunities to test out different things. So remember, I'm going to go, they just give it to us and ask us to find the antiderivative. So I always go like, okay, so this is a derivative. I'm trying to find the thing that came before. Okay, so I do that. So what would be my function? What's my best guess? Well, what is sine the derivative of? Cosine, right? If I take cosine, I will get a sine. I heard someone. If I take cosine, I'm going to get negative sine. I don't see a negative sign there, so yeah, you're right, you're on the right track. Sometimes you don't catch this right away. You just say, okay, it's going to be cosine, and you move on. But if you're thinking, wait, cosine is going to give me a negative sign, that's a positive sign, so I better make this a negative. Does that make sense? Because I need a negative times a negative to give me a positive, right? See this, and again, we might not catch it here, but if we didn't, we'll take the derivative and we would say, oh, I would have got negative sign, need positive sign, so then I could make the adjustment. Okay, that was my plan, but you guys spoiled it because you got right on it. You knew it was going to, that's okay. Okay, so this is going to fix it. And again, there's no right way to do this. It's just kind of go through and do your checking. So cosine, what's the thing that gives us cosine if we take its derivative? Sine, derivative of sine is cosine, and it's positive cosine, so I think we're going to be okay with the signs when we go through here. Again, we're going to do a check. We're going to take the derivative, make sure we get back to where we started with. And then 2 secant squared of x. What's secant squared the derivative of? Tan x. Okay, so this is one you have to kind of remember. I was going to put tan x, but then there is nothing that directly gives us the derivative tan x. We will deal with that later on, but you're going to see not everything integrates, or the antiderivative is not necessarily easy to find, or we're going to get some techniques to get us back to that. So if it's these simple things that we've got, the first sort of derivative is out there, like secant squared, the 2 can just hang on as a multiplier, and so we're going to give this a try. So what I do is then to check it, I take the derivative of the function I found. So cosine, So I've got negative cosine. If I take that derivative, I'll get negative sine, but I get negative sine, right? I'm going to write that out. Negative sine x, which will become positive sine x, which, okay, that's looking good, step by step. I got negative sine x. If I take its derivative, that'll give me cosine x, and the negative will just stay there, right? Because it's positive cosine x. Okay, that's looking good. And then 2 tan x, well, derivative 2 is just a multiplier, so that sticks along. Derivative of tan x is secant squared x, which is what we had, so it works. But I forgot something, didn't I? Told you I always forget this. Plus c, yeah. So it's, and I didn't do that on purpose. That was a natural. Plus a c. And hopefully when you do this, you see, okay, there could have been that plus c. Okay? Maybe if you want to, if up here you always go plus 0, that might help you to remember that c. I just thought of that. I should have thought of that like 30 years ago, and I wouldn't probably have that problem. But, okay. Just came to me. 30 years late, but okay. We doing so good? So far, so good?
How does the negative cosine turn into negative sine?
So negative, this one here?
No. Yeah.
This one up here.
Yeah.
So this negative cosine, what I'm thinking, to get cosine x, how do what would I take the derivative of? I know if I took the derivative of sine x, if I take this derivative, I'll get cosine x. So, but since I want negative cosine x, you say, oh, I better put a negative on better be negative sine x, and that'll give me negative cosine x. Does that make sense? So some of these is kind of just afterwards, you kind of figure out match things up. That's what I call it. It's not necessarily a set way of doing it. Okay. And again, a lot of this is just, there's quite a few problems that they'll give you. I think there's 18 or 20, but they're pretty short ones like this where you're undoing it. There's going to be a few challenging ones. We're going to look at that as our next one. Exponential and logarithmic functions actually can be a little more challenging. And again, just a reminder, what we're given is a rate of change. It is a derivative. So we're going to come back here. And that's another part of the problem I have is when I go both directions, I sometimes forget which way I'm going, right? Am I finding the derivative or am I taking the derivative? So you got to be careful here. So what kind of a function would give me 5 to the x as a derivative? I think I heard it. 5 to the x, right? Because it's sort of its own derivative. But if I take this derivative, 5 to the x, what else do I get? I get an ln of 5. I get it multiplied by an ln of 5. I don't see it up here, so anyway, I'm just kind of thinking ahead, and you might do it now or you might do it later. I'm going to need to maybe divide out a natural log of 5. So, because if I take its derivative, 5x, there's going to be this natural log of 5 that goes down, and a lot of times I would do that on the back end. Okay, so does that make sense though? That there's supposed to be a natural log of 5, because if you take its derivative, it is. Okay, this next one maybe is a little easier. So the negative, sometimes I just say, okay, let's leave that negative there. What would give us e to the x? Just e to the x? Yes, it's its own derivative. This is the one, so it's sort of easy, but it's also sort of, how do I know I don't need anything else? It's its own derivative, okay? So that one's, yes.
Okay, I'm like a little confused on like the ln of 5.
Okay.
Because like, if like it's 5 to the x, like the derivative is 5 to the x ln of 5, right?
Right.
So like, how does ln of 5 go back into the original equation?
Okay, so what I'm thinking, good question. Let's do this. I don't know I can explain it real well, so I'm going to ignore it for right now. So if you see it, that's okay, you could do it here. I'm going to just say, let me say I forgot about it, it'll be more natural when we take its derivative. It'll say, oh, that's why he did it. Otherwise, it's going to be kind of conditioned. Okay, but I know it's 5 to the x. I need it to start with 5 to the x. E to the x. I need e to the x. How about 1 over x? What is that the derivative of? Natural log ln of x. Like, so this is kind of this can get a little crazy, but it is right. If we take ln of x, when we take its derivative, we get 1 over x. Now, what's another thing I could have tried? I could have rewrote this as x to the minus 1. And if I take that derivative and I try to use sort of exponent stuff, and I say, okay, take the exponent down, and then oh wait, wait. So I could rewrite as x, no, I'm not taking the derivative of this. This is the derivative of something. This is what I mean. It's hard, it goes, okay. So this is x to the minus 1 is the derivative of something. If I try to think back, like what I was doing, if I add 1 to the exponent and then divide by that new exponent, ooh, that looks like it's not going to be very nice. It's going to be x to the 0 divided by 0. That doesn't work. So it's just, I have to remember 1 over x, it came from natural log of x. So we've got to see that that's where it is. Now this is where, I'll just put it out there. I'm going to make a mistake. So I'm thinking, okay, that works for 1 over x. Does that also work for 1 over x squared? Is this just going to be some kind of like natural log of x squared? What do you think? Not really, because if we take this derivative, right? So let's just pretend that that's what we thought it was. Okay, if we come back and take its derivative of what we've got, and again we would have a plus 0 here. Derivative of 5x is 5x. Oh, but there's that thing, natural log of 5. And when I look at this, that's not what I have, right? I don't have natural log of 5x, 5 to the x. I just have the 5x part. So what do I need? I need to go fix this. I need to divide out the natural log of 5 so that it will become, so that it won't show up in the final. Natural log of 5. So then when I put that here, these guys cancel. Now I've got what I started with. So that's what I mean is sometimes we just kind of go through and then we're sort of fixers. That's not quite right, but we're close enough. We can fix with constants. Okay. One thing we can't fix with is variables, and you'll see that on the last one. You'll see I have a problem with the last one. So this one works out if I leave it as is. Take the derivative of e to the x. What do I get? I get minus e to the x with nothing. Okay, so that one's looking good. Okay. Take the derivative of natural log of x. I remember that is 1 over x. Ooh, that's good. Okay. And then I take the derivative of natural log of x squared. Now I could bring the 2 down in front, right? If I do that, what do I get? I get 2 over, actually that shouldn't be plus, right? It should be minus. So let's do that. I get 2, and then derivative of natural log of x is 1 over x. 2 over x, but I've got 2 over x squared. You see, this didn't work. It didn't give me the right thing. The thing is, this is the one I should have looked at this as x to the minus 2. So I wanted you to see the difference. If I just have 1 over x, its antiderivative is going to be natural log of x. But if I have 1 or something over x squared, I want to think of this as x to the minus 2, and this is a polynomial type function where I can, that's not really, but we'll call it that, because polynomials don't have negative exponents, right? But it's got an integer exponent, let's put it that way. So I can add 1 and then divide by the new thing. So what I do is add 1 and divide by that new exponent. That's the thing that's going to work. So I'm going to cross this out. I don't want to erase it. If I put this in, that's going to give me x to the minus 1, 2x to the minus 1 divided by, what's that, minus 1, right? Let's see if I get that right. 2 x to the minus 1 divided by minus 1. So we're going to need to clean up here a little bit. So go ahead and take this out because let's try that again. So 2x to the minus 1 divided by negative 1. There's that negative. And so I haven't cleaned it up yet, but before I clean up, right, I always want to check. So this was wrong, so we could take it out. So notice I've got this negative is down there. I've accounted for everything here. So if I take this derivative as it is, right, taking a derivative, the negative comes down, negative times 2 is going to give us a plus 2. We're dividing by negative 1, so that's going to change it back. We got another negative in there, change the positive to a negative. And then when I subtract 1 from this exponent, I'm going to get x to the minus 2. I got back to what I needed, right? Okay, so let's come up here. The function should be 5 to the x divided by natural log of 5. Again, remember that's kind of like the constant is going to go out. Minus e to the x, that was okay. Plus 1 over x. And then we're going to get, what do we end up with? We end up with a...
Isn't it plus
I think it's
plus. Oh, thank you, thank you. So you had to catch yourself on it. So you go back and forth and then you forget which one. Yeah, let's circle. This is the function we worked with. I was confusing myself because I was looking at my checking function, and thank you for calling me out on that. It needs to be plus ln of x. Good. And then looks like we ended up with, did I get this minus right?
I think it's a plus 2x raised to negative 1.
Yeah, because that's what I was thinking, because we're going to get the negative coming down from the exponent. So somewhere in here, this should be, I guess, if you, oh, a negative and negative make a positive. I think that's, it's okay, so we cancel this out. So it should be plus 2 over x. Okay, which is, again, a little confusing because you're thinking, isn't that supposed to be logarithm? But remember, this is the function we're taking as a derivative. So when you're taking 1 over x as a derivative, you end up with x to the negative 1, you subtract 1, you get x to the negative 2. Okay? So if the derivative has 1 over x, then the antiderivative is going to be natural log of x. If the original function it comes from has a 1 over x, a 2 over x, when you take that derivative, remember that's an x to the minus 1, it'll become x to the minus 2 because you're subtracting the exponent. It's something you just kind of have to work with. It's something you have to say, it's going to be a little confusing, it's going to be a little bumpy, but I'm going to check it, go back and forth, and eventually I'll get it. Okay, and then remember, plus a constant. Most of the examples will be shorter and they'll kind of focus on one of these. I'm just kind of want to take an example where I could pull out a lot of different types of things. Okay. We doing okay now? Still a little less comfortable than that first example, so we can see how it is. Actually, this opened up in the wrong order, but we'll show this. So this is just sort of a formal definition from the textbook. So we're going to use the big letter F to be the antiderivative, the function that the derivative comes from. Okay, and then the theorem below that says, yes, every time we get the antiderivative, the general form is going to have a plus c, because if you have a constant, when you take its derivative, it becomes 0. Now, c could be 0. You just drop it off, right? But it might be something else as well. So it's just kind of a reminder. So it's just kind of, yeah, if you take, once we get our antiderivative, if we take its derivative, we should get back to where we started. So again, in algebra, this is equivalent to foiling and then factoring, right? Foiling out, we get a polynomial, we factor it, we've refoiled it, so it's kind of like going back and forth between there. In calculus, we go back and forth between the derivative and the antiderivative, okay? And again, the reason we do this is just, well, why are we taking all these derivatives? Sometimes, again, the function we have, we've measured a value of something, you know, and so we want to find how quickly things are changing, so we take its derivative. Other times, our measurement is actually the rate, how fast are things changing, and then we want to have some understanding about what's happening with the original situation, what's happening with the values of stuff. I know the rate my company is spending money, the rate of change of, maybe if it's, you know, if I lose maybe my profit, I know the rate of change of my profit. I want to see where my final profit's going to end up, right? So that's what, you know, it just depends on what we're measuring. This is in the textbook as well, and this is, you might want to either print this out or sort of write some of these out, because it's going to make it easier. So you're going to see the, again, when they're talking function, this, remember, these are all derivatives down here. So these are the things we've been getting as derivatives. These are the antiderivatives, or the things they came from. So if I take the derivative of tangent, I get secant squared. In our homework, we're going to see secant squared x, and we're going to be asked to answer it. It came from tangent x, right? So we've got to see these things, and these ones, again, you might try to think of them as, how do I, you know, as a polynomial function or something, or a quotient rule thing or something. No, it's got to have come from the inverse tangent. We don't do anything, or we haven't been doing anything with hyperbolic cosine or hyperbolic sine, so I think we can safely ignore these. That's a section we skipped. It's got a few rules in here, but here's this thing, right? Just like we were doing, add, when you want to find it, add 1 to the exponent and then divide by that new exponent. So that's exactly what we were doing. Gets us back. These two are pairs. So again, what you're looking at is the pairs. When you see 1 over x, you know that it's going to be natural log of x. And again, yeah, technically it should be absolute value of x, because you can't have negatives inside of a logarithm, but sometimes we get a little sloppy. E to the x is e to the x. So these are just, you know, again, going back. But maybe make your own little table of this as you go through things, and it'll make it easier to see, I'm just going backwards. These are the things that I can do. Okay. A few more examples just to kind of give us a little bit more of a challenge. How about this one? What do you think we should do here? Is this going to be a natural log of something, maybe? No, because it's not 1 over x. So we can rewrite this with an exponent, right? So I think the first thing I would do is write this as 1/4 u to the minus 1/2. So I moved it up to the upstairs. And then now let's see, okay, if I've got an exponent, how do I get its antiderivative? Let's try going backwards, right? To get the derivative, I subtracted 1. I brought the exponent down and then subtracted 1. So for antiderivatives, I'm going to add 1. I'm going to add it as 2 over 2. This makes it easier with same. And then I need to divide the whole thing by that new exponent. Let's see what we get. So negative 1/2 plus 2 over 2 gives us u to the positive 1/2. Still have this 1/4 in the denominator. I'm going to get positive 1/2. Let's see, this 1/4. And so let me see. I invert and multiply, so the 2 and 4, does it look like I'm going to get the square root of u over 2? Yeah. 1/4 invert 2 over 1. That's going to give us 1 over 2. Okay. So what do I need to, and plus a constant, right? What do I need to do to make sure that this is correct? Take the derivative. So I'm going to rewrite this as u to the positive 1/2 over 2. And I'm going to take its derivative, so I'm going to first subtract 1. No, I'm first going to multiply by the the exponent, right? I'll multiply by 1/2. Then I'm going to subtract 1. So 1 over 2, think of this as 2 over 1, so if you invert it, you get 2 times 2, which is 4. This is going to give us u to the minus 1/2, which when I move it downstairs, there's a factor of 1 left upstairs, 4 square root of u in the bottom, and that's what I started with, okay? And again, the constant becomes 0, so this is our check. This is our answer. This is our antiderivative. Okay, so give it a try. And they may not all go real smoothly, but you can the nice thing about this is you can always check it. When factoring, you can always multiply to check it. But how many of you do? I'll be honest, I don't always do it because I think I'm right, and then I find out later I should have checked it because I was off by a negative sign or something, right? So do check them. Take your time through there, or don't, but just, maybe on the test, check them. So it's just, it'll help. Here's another one, and I did this one on as well because, so t to the minus 1. So do we try to add 1 to that exponent? You could, but then you get t to the 0, right? And when you divide by 0, ooh, that's not going to work. So what's another way to write t to the minus 1? 7 over t. Now that should give some kind of indication. What is this the derivative of? Natural log. And again, they were kind of nice. This isn't from the homework, as you can see. They're telling us this is a derivative. Okay, we're trying to find the thing it came from. So just be careful, just because it said us t to the minus 1. It's really 1 over t. So this first part we're going to say is 7 natural log of t. Okay, and we'll check it, and it will work. How about plus 3? What would give us a derivative of 3? 3 to the t. So again, with this one, you might want to write t to the 0. Add 1 to the exponent, you'll get t to the 1. Divide by 1. Plus c, right? And then if you check it out, so this we're saying is the antiderivative function. You're doing good. If you take this derivative of the first part, derivative of natural log of t is 1 over t with a 7 over t. Take the derivative of 3t, 1 comes down, you get a 3. Derivative of c is 0, so it worked. Okay, so it's a guess and check process. I've got, I think, 1 or 2 more. I guess 2 more. The approach is a little different. So with this one, what does this look like it might have come from? Inverse tangent. So that's the thing you want to see here. Otherwise, if you don't, these just have to be fresh in your mind, because otherwise you look at this and I don't even know where to start, right? And you'll get down the road next week, and you'll probably do fine with it now, but next week you'll probably have forgot, at least if you're like me. You'll forget, and then you'll try to do some funky stuff with this, and say, oh, it's just inverse tangent. So, but what about this 5? It's just a multiplier, right? So we could say it's probably 5 arctangent or inverse tangent, if you want, of just x, right? And then you could try, okay, let's take this derivative. That's going to give us 5. Derivative of inverse tangent is 1 over 1 plus x squared. Yep, the 5 can go on the top. It works. Okay. So again, just kind of recognizing some of these. Once you sort of recognize them, it's pretty straightforward. But if you don't recognize them, it's like, where do I even start? You go look back at the derivative tables. Okay. How about this one here? What's that? Sorry. Okay, yes. So we want to do a little bit of algebra first. So sometimes we could do this. So this is, remember, this is a derivative of something. Let's break this down. Let's divide both of these by x. So we'll rewrite it as 4 over x minus 2x e to the x over x. So the x's cancel here, right? So this is now just 2e to the x, not bad. And we want to get the antiderivative, right? The function it came from. How about 4 over x? You see that as being a natural log, a derivative of a natural log. So that's got to be 4 natural log of x. Okay, so a lot of these things you have to know your derivatives back and forward. How do you know that 12 divided by 3 is 4? Memorize that 3 times 4 is 12, right? So this is part of it. It's just you've got to know these things. And then how about negative 2 e to the x? Well, just remember e to the x is its own derivative, so we must have minus 2 e to the x. The negative 2 just tags along for the ride. And then we always have that possibility of having plus a constant. Again, take that derivative, you'll get back to where you started. You're in good shape. That's all there is, I think. Yeah, nothing more. All right. Have a nice Veterans Day. Be sure to thank any veteran you know for their service. I can't hear you. Is there an error up there? I think so. I do. And I have office hours if you want to come. I'm capped until 6 o'clock tonight. I have a class, so. Yeah, there's always a plus. Like I said, I always forget it. Yes, thank you. Yes. Always a plus. Way after, so yeah, after we've kind of completed the courses, and that you're going to be at your best derivative skills. Yeah. So I want to catch you.